In today's class, we're going to finish up our look at Chapter 7. In a previous class, we introduced the idea of effective nuclear charge and used that to predict the size of atoms and ions. We're going to extend that idea now to look at other properties, including ionization energy and electron affinities, and from there put it all together to look at some patterns that we see on the periodic table. So to review, when we're thinking about the size of atoms and ions, if we first consider neutral atoms, we see that there is an increase in size as we move down the periodic table because the atomic orbitals have a larger and larger principal quantum number. And if we're moving left to right, the quantum number stays the same, but because the effective nuclear charge is increasing, it leads to a contraction in size. If we consider anions and cations, anions become larger than the neutral atom because we're adding electrons, which repel each other. Cations are going to become smaller because we're removing those electrons that were repelling each other. We also introduced the idea of isoelectronic, which meant the same number of electrons, the same electron configuration, but we have a different number of protons. And the different number of protons led to differences in size that we could predict. At the top of that slide, I summarized those factors. Let's use that to complete the table. The different comparisons there illustrate different features that influence the size. So take a moment, try to complete the table. What is the reason and what is your prediction? So here we have many different examples. In the first case, it's a comparison based on effective nuclear charge. The second involving the principal quantum number. We had examples using anions and cations. We have one where the effective nuclear charge is increasing, but the same principal quantum number as we compare from lithium over to neon. And then finally, a case where we had neon as a +2 cations, a +1 cation, and then as a neutral atom. If we're able to predict the size, we're going to be having a great head start on being able to predict other properties as well. We've mentioned making ions. What's the electron configuration of an ion? For an anion, it's pretty easy. Electrons will be added to the available energy level that is lowest in energy. So if I look at fluorine, it's 1s2, 2s2, 2p5. To make the fluoride anion, we would add it to that available 2p atomic orbital to make it 2p6. For cations, electrons are always going to be removed from the energy level that's highest in energy, and that's based on the principal quantum number. So we need to be careful here with our transition metals. Give this a try. So if we're thinking about iron becoming a 3+ cation, as a 3+ cation, what's its electron configuration? How about gallium? What is a electron configuration for gallium? And then gallium as a +1 cation. With iron, we're going to remove 3 electrons to make it a 3+ cation. I remove from the ones with a higher principal quantum number, which means I'm going to remove from the 4s before I remove from the 3d, so the resulting configuration would be argon core 3d5. For gallium, the highest occupied is in the 4p1, and that's what I would remove. So we need to be careful, especially with our transition metals, because the 4s is higher in energy than the 3d. The energy involved with producing these cations, that's the ionization energy. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. Gaseous is being introduced there, included in there, because we want to be thinking about the atoms just themselves, not the atoms bonded to other atoms. So the expression that we would have would be the gaseous atom to produce the cation plus an electron. The symbol for the first ionization energy, which means removing the first electron, is this I1. In these two examples, these are both large positive numbers, both very endothermic. It takes a lot of energy to remove an electron because there's an overall attraction that we have between the protons and those electrons. And that's what we need to overcome. Now, you can remove one electron, and then you could remove a second, and then a third, and then a fourth. These are the successive ionization energies with symbols I1, I2, I3, and so on. Ionization energy is really closely related to size. The smaller the size for an atom, the greater the attraction for those valence electrons. And if there's a greater attraction for the valence electrons, that means it results in a higher ionization energy. So if we can determine the size for an atom, we can also determine its relative ionization energy. Consider these 4 groups of data. So in each of these cases, we have different ionizations taking place in the resulting experimental data. Can you explain the trend in size for each group? They're being used to illustrate different features. Remember, if you know the relationship between ionization energy and size, this ionization energy is telling you something about the size. The ionization energy is largest in this group for hydrogen and smallest for potassium, which means hydrogen is the smallest of the atoms and potassium is the largest. Why is that? Can you explain the trends in size for all 4 groups? Within group 1, it's illustrating how we have larger and larger principal quantum numbers moving down a column, which is leading to an increase in size. In group 2, here we're forming a +1 cation, then a +2, +3. These are the successive ionization energies. Cations are smaller as electron-electron repulsions decrease. Over here in group 3, we're moving left to right, so the effective nuclear charge is increasing. And group 4, here's another example where we're making +1, +2, +3 cations. And so along the way, cations are becoming smaller and smaller. Take a moment. We have 2 examples here involving successive ionization energies, removing the first, second, third, and fourth electrons. Make a plot of those. What do those look like? And it's going to help if you put them on the same scale. Here's my work showing them on the same scale. Within neon, we see a steady increase in the ionization energy as the cations are becoming smaller and smaller. Over here in beryllium, we see an increase and then we see a huge increase. What's going on here? When we try to remove the third electron from beryllium, we're now removing an electron that is from a smaller principal quantum number. It's closer to the nucleus and it has a higher effective nuclear charge because the shielding has changed. So we have this very large, disproportionate increase when we're now removing electrons that are in a smaller principal quantum number. This figure shows some more ionization energy. The data is shown for different elements. So take a second, try to answer these questions. Why does helium have the highest value? Why is the value for nitrogen a little higher than the value for oxygen? And related to that, find beryllium and boron. What explains their relative values? For the first one, helium only has 2 protons, but the electrons are found in the n equals 1. They're very close to the nucleus. So even though it only has 2 protons, the overall attraction is greatest. Helium is our smallest neutral atom, and it also corresponds then to the one with the highest first ionization energy. What about these comparisons involving nitrogen and oxygen, and then beryllium and boron? We need to look at these a little bit more closely. I show here the electron configuration for all of the ones that I'm comparing. So first of all, nitrogen and oxygen. I don't really get insights as to why oxygen is a little smaller than I would anticipate for its ionization energy simply on the electron configuration. But if we use the orbital diagram for them, that reveals the answer. With nitrogen, it's 2p3. With oxygen, 2p4. Notice within the orbital diagram for oxygen, I had to begin to pair up 2 electrons in the same atomic orbital. I'm putting a negative charge in the same region of space where I already have a negative charge. That's going to slightly raise the energy. And that difference, it turns out in this case, ends up being important. And it's a little easier to remove that additional electron in oxygen compared to nitrogen. How about this comparison involving beryllium and boron? The difference there is that we're removing from boron an electron from the 2p. With beryllium, we're removing it from the 2s. In our simple shell model, we can say that n equals 2 for both the 2s and the 2p. But we know that's not exactly true. We know that the 2p is somewhat higher in energy, and because it's higher in energy, it's a little easier to remove it from the 2p than we would have anticipated compared to removing it from the 2s. With electron affinity, we're now adding electrons. With an electron affinity, we need to ask, where is the electron added? With ionization energy, we ask, where is the electron removed from? But with electron affinity, we have to think, where is that electron going? So in this case, it would be clear that, okay, it would be going to this available 2p atomic orbital. What are the energetics involved with adding an electron? Here we have two different equations for electron affinity. In both cases, we're starting with the atom in its gaseous state, and we're adding the electron to make an anion. The greater the attraction that we have between the atom and that additional electron, the more negative the electron affinity. A favorable electron affinity is negative. An unfavorable one is positive. So what leads to a more favorable electron affinity? The electron that is being added, I'd like it to be close to the nucleus and to experience a large effective nuclear charge. What would reduce the attraction and make it unfavorable? Well, we could look at the opposites of these. Instead of being close to the nucleus, it could be far. Instead of a large effective nuclear charge, it could be small. It's also unfavorable to pair electrons in the same orbital where I already have electrons. Now, we have some competing factors there. For a given electron affinity, more than one thing might apply. And these competing factors lead to a less clear trend compared to the ionization energy. Some of the values that we see listed here are positive and some are negative, and they have quite different magnitudes. When it comes to electron affinity, we're not going to be asked to predict a general pattern, but oftentimes to make some explanations. Given the experimental data, how do we explain it? So let's give that a try for a few examples. It's favorable to add an electron here to hydrogen because I see a negative value, but unfavorable to add it to helium. Positive value. Well, why might that be? If I'm adding an electron to hydrogen, hydrogen is initially 1s1. Here's a shell picture for that. The additional electron, well, I could also add it to the 1s. It would be close to the nucleus. There was an initial attraction for the electron that was in the 1s, and I'm adding another electron to that same shell that's available. I can see why that would be favorable. How about for helium? The two electrons initially there are close to the nucleus, but if I add an additional electron, it can't go close to the nucleus because I've already filled up the 1s. It has to go farther away and fill up the 2s. Farther away from the nucleus, that's not going to lead to a strong attraction. Similarly, what would be the effective nuclear charge if I add that? If I've added an electron here to the 2s, its effective nuclear charge would be 2 protons minus 2 shielding electrons. The effective nuclear charge would be 0. There is no reason to add that electron to the 2s. It has no net attraction there. That's why we have this positive value for helium, and the same reasoning applies for any of our noble gases. We would always be adding the electron to a higher principal quantum number, and the effective nuclear charge would be 0 in each case. How about something like fluorine? Within fluorine, we have a high effective nuclear charge for the electrons initially there. We can add another electron to the same shell, and that one that we add would also experience a high effective nuclear charge. That's great. That would be very energetically favorable to add an electron here to fluorine or for any of the halogens. Those are the most negative, the most favorable additions. How about nitrogen? Nitrogen has a positive value, which means it's unfavorable to add an electron. Here would be the orbital diagram. for nitrogen, if I add an electron to make the nitrogen minus anion, why is this unfavorable? As I look at it, I'm back to the idea I've had to pair up two electrons in the same atomic orbital. And it turns out in the case of nitrogen, that leads to an overall unfavorable electron affinity. How about this comparison? It's favorable to add to lithium, but not beryllium. Lithium is 1s2, 2s1. Beryllium, 1s2, 2s2. We ask the question, where's the electron going? For a lithium minus anion, it's populating the 2s. For the beryllium, the 2s is filled, so it needs to fill the 2p. This is back to the idea that the 2p orbital is a little farther away than the 2s. And it turns out in this case, that makes it an unfavorable addition, whereas if I'm adding to lithium and I'm still populating the 2s, it's favorable. One more scenario to consider. How about oxygen? It says oxygen has a negative exothermic electron affinity. Okay, that makes sense. If I'm making an oxygen minus anion, I can put the electron into the 2p. The electrons there, we're experiencing a rather large effective nuclear charge. I have space to add another electron, and it would also experience a large effective nuclear charge. So it makes sense why that would be favorable. But what if we were to go on? What about the energetics to make it oxygen 2 minus, to make it 2p6? First thought would be, okay, I have room to put it there. However, something else is going on. To make it oxygen 2 minus, I'm trying to add a negative charge from the electron to a negative charge for the anion. It is not energetically favorable to add a negative charge to a negative charge. It's never going to be energetically favorable to add a negative electron to a negative anion. Now we're going to need to learn more. Okay, we will learn more in chapter 8 to seek to explain why we often find oxygen as an oxygen 2 minus anion. And for that matter, why is nitrogen often a nitrogen 3 minus anion? If it's unfavorable to make oxygen 2 minus, it's going to be really unfavorable to make nitrogen 3 minus. So we need to learn more. Let's wrap up by taking some of these ideas and thinking about them more big picture, and consider how the properties of the atoms themselves affect the properties when we have a collection of atoms. Here's our periodic table showing the regions that are metals, nonmetals, and metalloids. Most of the periodic table are metals, especially as we see towards the left-hand side. Now, would metals have a high or a low ionization energy? I'd say they're going to have a low ionization energy. We've seen they form cations, and we'll also learn how they can be found in nature as metallic elements. Alkali and alkaline earths, they're in our first two columns here. They have very low effective nuclear charges, so that's a reason that we can explain why they would have low ionization energies. If we look here, we see that oxygen, sulfur, those become 2 minus anions when we find them in ionic compounds. And that would be a case where we need to learn a little bit more about why that occurs. If the second electron affinity is unfavorable, how does this occur when we have a collection of atoms in an ionic compound that this becomes 2 minus? That's an idea we'll look at in chapter 8. Now, there's very contrasting behaviors for reactions in water when we think about metal oxides and non-metal oxides. So in order to remember this, it helps to have two clear examples. A metal oxide would be something like sodium oxide. It reacts with water to produce sodium hydroxide. That's a base we've definitely seen before. Metal oxides react in water and they produce a base. How about non-metal oxides? Let's consider carbon dioxide. That's nonmetals. It reacts with water and it forms carbonic acid. That's a weak acid we've seen before. Now, this chemistry involving the formation of carbonic acid, this is hugely important on our planet. It's one of the most important reactions that's taking place right now, because the carbon dioxide that's being produced through combustion reactions. It's going into the atmosphere, and right now, a very large amount of it is being absorbed by the oceans. This is a way that the carbon dioxide is being stored, and that's very beneficial to try to reduce the rising of the Earth's temperature due to greenhouse gases in the atmosphere. However, as it's going into the oceans, it's also changing their acidity. Carbon dioxide is being produced, it's forming carbonic acid, and that's now changing the pH of the oceans. This is affecting the life forms there, including the coral reefs. It's showing, in this case, this progression as more and more carbonic acid is being formed within the oceans of how it's causing the death of coral reefs. Very important chemistry taking place in the world around us. We see at the end of chapter 7 tables like this. They show different properties for different columns of the periodic table. I sub 1, that's what we've been talking about as the ionization energy. That's a property of the atom itself, a gaseous atom. How about things like melting point and density? Are these properties of an atom or when we have many atoms together? What do you think? Both of those are properties for a collection of atoms. When we say that a substance has a melting point, the atom itself is not melting. We're instead changing the arrangement of the atoms and considering how they could be arranged as a solid or a liquid. Turns out the density is the same thing. The density here refers to a collection of atoms, how the particular atoms are arranged in a solid. At the end of the chapter, we have similar properties listed for the right-hand side of the periodic table. Group 6A, which includes oxygen, and then the halogens and the noble gases. Just a couple takeaways here. If we look at the data for the melting point, considering the halogens, for these diatomic molecules, the diatomic molecules are more and more strongly attracted as we look at as the atoms have a larger and larger mass. Fluorine, chlorine, bromine, iodine, we're moving down the periodic table, and notice how the melting point is going up. Fluorine and chlorine are gases, iodine's a solid. So we see this progression that the diatomic molecules are becoming more and more strongly attracted to each other as we move down the periodic table. Similarly, if we look at the noble gases, notice how their boiling points increases. The atoms themselves are more and more strongly attracted to each other as we move down the periodic table. This is something that we're going to develop an understanding of, and it's going to be discussed in chapter 11. Before that, well, why are the halogens themselves diatomic molecules and the noble gases are not? Why are the halogens bonded together, but the noble gases exist as individual atoms? What leads to bond formation? Really important chemistry idea, and that's what we begin to explore next chapter.